Good morning, class. Let's start our lesson today. In the previous chapters, we have learned about the kinematics and dynamics of one-dimensional motion. We have investigated the displacement, speed, velocity, accelerations, forces, and Newton's law of motion. In this lesson, we will examine a special kind of two-dimensional motion, that is circular motion. We will investigate the kinematics and dynamics of circular motion. So, let's first define what we mean by circular motion. So, circular motion is motion in a circle of constant radius r. Let's take some examples of circular motion. In our everyday life, we see circular motion in a rotating bicycle wheel or a rotating ceiling fan. In amusement park, the Ferris wheel and the merry-go-round are just two of many examples of circular motion. In large scale of the universe, satellites orbiting the Earth and the planets orbiting the Sun in our solar system are also examples of circular motion. So we see that circular motion occurs everywhere around us, from the very large scale of the universe to the very small scale of atoms. Now, let's investigate the kinematics of circular motion. Consider an object which can be treated as a point mass travels on this circle of radius r and center O. It starts from A and travels along this circle to the point B. The total distance it covers along this circle is s. And during that time, the radius vector, which is the vector connecting the center of the circle and the point mass, rotates an angle theta. That angle theta is called the angular displacement of the motion in that period of time. So, we define angular displacement theta is the angle through which the radius vector sweeps as the object moves in the circle. Let's see how this angular displacement theta relates to the total distance as the object travels. Think about an object traveling a full circle. Then its angular displacement is 2 pi radian. And the total distance it covers is the circumference of the circle, which is 2 pi r. We see that there's a radius r multiplied by the total angular displacement to be the total distance. So in general case, when an object just travels an angle theta, then the distance it covers is theta times r. And that is the distance. So we can say that the angular displacement theta is equal to s divided by radius. And hence we have this relation. And in this relation, theta has the unit of radians only and not in degrees. Now, the faster the object travels on this circle, the faster the radius vector rotates, and the faster the angle theta changes with time. So we can use the rate of change of theta with respect to time to represent how fast or slow an object is traveling on a circle. And that quantity is called the angular speed of the circular motion. Angular speed is the rate at which the radius vectors rotates. And to derive the equation for angular speed, omega, we will take the change in angular displacement over the change in time. Or in other words, the derivative of angular displacement with respect to time. So we have this relation. And according to this relation, angular speed will have the unit of radian per second. We have learned in one-dimensional kinematics that speed only tells us how fast an object is traveling. But velocity not only tells us how fast an object is traveling, but also it tells us in what direction the object is traveling. So now we know how fast an object is rotating, and we want to know in what direction with the velocity vector of the object points. And to know that, we will do a simple experiment. On your table, you will see you have a plastic cup and a little marble. Newton's first law says that if an object is going under the influence of several forces, and then suddenly the forces disappear, the object will continue to move in the same direction and the same speed as it does before the forces disappear. And let's do that. I will put the marbles inside a cup, upside down cup like this, and I will rotate the marble around the cup. And then I lift the cup to set it free. And then it will continue to move with the velocity that it has before I lift the cup. And we will know which direction it will move. Okay, let's see. Again. As I lift the cup, the ball is right here, and I lift the cup, and it travels in a straight line. To make it more clear, let's look at this device. It has a gap over here, so when I rotate the ball around this ring, it will escape at this gap, and we can see in what direction it travels. So let's see it again. You see that it travels in a straight line from here to there. And this line just touches the circle at this point. In other words, we say that this line is tangent to the circular path at that point. So we conclude that the velocity vector of a circular motion is tangent to the circular path. And because of that reason, we call it tangential velocity. And because it's tangent to the circular path, it is perpendicular to the radius vector. Once the object travels from A to B, its velocity changes direction so that it is tangent to the velocity to the circle at B. So we have this direction. And as it continues to move, the direction of velocity changes until the point C. And again, it has a tangent direction to the circle. That is about the direction of velocity. Now, let's look at the magnitude of velocity. You know that velocity is the rate of change in time of displacement or distance. So I have distance s equals to theta r. I'm going to take the time derivative of it to get velocity. I'll do that here. ds over dt. And that is d of theta r over dt. And because the radius r is a constant, so we can take it out of the derivative. And remember that d theta over dt is the angular speed, so we can write r omega. And hence we have the relation v equals r times r, omega. V is in meter per second because it's velocity. This property is true not only for circular motion, but also for any curved motion. So the velocity vector of any curved motion at any point is tangent to the curve at that point. Knowing that, let's consider this curved path and an object traveling on this curve passing 4 points A, B, C, and D. And I want you to spend 30 seconds to draw this picture on your notebook and draw the vector, the velocity vector at these points. Let's do that. Now, I'll give the answer. Here are the velocity vectors. They may not have the same magnitude, but they must have the same characteristic. That is, they are all tangent to the curved path at that point. Here are some real-life examples of that situation, of that properties. A race car approaching a corner, and because of friction between the wheels and the road, it can make the car can make a turn across at the corner. But if that friction is not large enough, then the car will travel with whatever the speed it has over here, the same direction, same speed. So it tends to make this kind of path, as you can see some of the skid marks show. And in this picture, the tiny bits of metal flying out of the greenstone at this point make a tangent line to the greenstone at that point. So you can find many of these kind of similar examples in your real life. Now I have a question for you to think about. The word uniform means that something is constant. Which of the following quantities is or are constant in uniform circular motion? A. Angular speed. Tangential velocity. C. Both A and B. D. Neither A nor B. Let's think about it for 30 seconds and then discuss to your friends around you in 1 minute and then vote your answer. Alright, now I will give the answer. To answer this question, let's look at this picture again. You see that this point mass is moving on a circle at a constant speed, which means that the magnitude of the velocity is constant along the circle. But the direction of velocity is obviously different for different points. So we will say that velocity vector has constant magnitude but continuously changing direction. And because of that reason, we know that whenever an object changes its velocity, either in direction or magnitude, or both direction and magnitude, there must be some acceleration involved. So we can say that uniform circular motion is accelerated motion. And therefore, we have to examine its acceleration too. Now, let's examine the acceleration. Consider a circle and a point mass moving on this circle. Its location is determined by the radius vector r. And for the purpose of finding direction and magnitude of acceleration, I'm going to introduce the Cartesian coordinates x and y, on which the position of the particle can be defined as r cosine theta on the x-axis and r sine theta on the y-axis. Then the radius vector r can be written as r vector equals r cosine theta I hat plus r sine theta j hat, in which I hat and j hat are just two unit vectors of the x and y axis respectively. To find acceleration, I have to take time derivative of velocity. And to find velocity, I have to take time derivative of this position. So let's do that. Velocity is equal to time derivative of radius. And that is equal to r is constant, time derivative of cosine theta is minus sine theta d theta over dt, because theta is also a function of t. So that is r minus sine theta d theta over dt of I hat plus r cosine theta d theta over dt j hat. And remember, d theta over dt is omega. So we can say that this is equal to r omega times minus sine theta I hat plus cosine theta j hat. So I have this result. Now, I want acceleration, so I'm going to take another time derivative of v, which is r omega constant, minus sine would become minus cosine theta d theta over dt I hat plus minus sine theta d theta over dt j hat. And again, I will say that d theta over dt is omega. So I can take that out, and I can take the r multiply in. I will have minus omega squared times r cosine theta plus r sine theta I hat j hat. The reason I do that is that now I have, this is the vector r as the beginning we have, and I have a vector equals minus omega squared times r vector. So I have this relation here. And acceleration is, of course, in unit of meter per second squared. Let's examine this relation a little bit. You see that acceleration vector is equal to a minus of a positive number of r vector, which implies that acceleration is in opposite direction with the radius vector. So here's the radius vector. So the acceleration vector would point toward the center of the circle. And because of that reason, we call it centripetal acceleration. In Latin language, centri means center and petal means seeking. So centripetal acceleration means that this acceleration is always looking toward the center of the circle. Here is the acceleration vector. And the magnitude of acceleration is just omega squared times the magnitude of the radius vector, which is the radius of the circle. AC equals omega squared times r. And if we think of omega as v over r, we will have v squared over r. This quantity, the physical meaning of this quantity is that it tells us how fast the direction of the velocity vector is changing. However, so this is the net acceleration of an object in circular motion. Newton's second law tells us that whenever an object experiences an acceleration, there must be a net force acting on it, and the relation is F net equals ma vector. So the net force that is acting on this object to cause it a centripetal acceleration is called the centripetal force. And that force has the same direction with A because m is a positive constant. So we have Fc pointing toward the center of the circle. And its magnitude is m omega squared r, or m v squared over r. Remember, centripetal force is the net force of all the forces acting on an object in circular motion. It is not a new kind of force. It is not a single force acting on it. It could be one of, or the sum of, all of these forces. Gravitational force, frictional force, tension, elastic force. Let's consider these examples. Here, the Earth is rotating in a circle around the Sun because the gravitational force between the Sun and the Earth provides the centripetal force for the Earth to rotate. A stone attached to a string and is swung in a horizontal circle. In that case, the force F here, which is the tension from the string, is the centripetal force. And in this case, the net force between the gravity and the tension force provides the centripetal force. When the car is making a curve path, then the frictional force between the wheels of the car and the road is the centripetal force. Because if there's no friction at all, the car will never be able to make a curve, and it will slide straight in the direction of its velocity. And in this final case, a mass m is attached to a spring and is swung in a horizontal circle. And the force that makes the m move in a circle, in this case, is the elastic force from the spring. Now, let's summarize what we have learned so far. We have learned the characteristic of the velocity, acceleration, and force acting on an object in circular motion. So let's summarize it here. The velocity has the direction which is tangent to the circle at that point and equals to r omega. Centripetal acceleration, as its name refers, points toward the center of the circle and is equal to v squared over r, or r omega squared. And the centripetal force is directed toward the center of the circle and is equal to mv squared over r, or mr omega squared. Now, I want you to spend 2 minutes applying these properties to draw the set of 3 vectors: velocity vector, centripetal acceleration vector, and centripetal force vector on this picture where a car is moving on a curve between A, B, and C. So let's draw 3 vectors here at A, B, and C. Let's do that in 2 minutes. Now, here's the answer. You see, force and acceleration toward the center, whether the center is below or above the curve. Velocity is always tangent to the curve. And right here, there's no centripetal force because there's no curve at all, and therefore no centripetal acceleration. By now, I hope that you have grasped the idea of velocity, centripetal acceleration, and centripetal force. I want you, after this class, to think more about it and answer these questions. Question 1. If an object is in uniform circular motion, then it is accelerating toward the center, yet the objects never get any closer to the center of the circle. So, suggest a reason of As to how this can be, how can an object continuously accelerate toward the center of the circle without ever getting any closer to the center? Question 2. Student A says that centripetal force is Fc equals mr omega squared. So a car making a wide turn with a large R circle needs a larger centripetal force than does a car making a sharp turn, which is a small R. And student B says that no, centripetal force is also written as Fc equals mv squared over R. So a car making a wide turn needs a smaller centripetal force than does a car making a sharp turn. So according to you, who is correct and why? Explain your reasoning. And the third task for you to do at home is to take a picture or make a video or make a toy from your everyday life which involves uniform circular motion, and point out on your picture, on your video, and on your toy the direction, the tangential velocity, the centripetal force, and centripetal acceleration. And please do those tasks on a separate sheet of paper and turn it into me in the next class. And our class today about circular motion is over. Thank you for your attention. See you in the next class.